Welcome again to this High Capacity Access Networks Insight webinar. Right, I just need to get some tools up here. Right, I think some of you are familiar with who we are and what we do. Certainly recognise a few names in the participants list here. But for those of you who perhaps have not heard of us before, we're of course Telecoms Academy, in former Telecoms Academy. And our purpose, if you like, purpose of the business is to deliver, of course, technical, non-technical training. So you can see the kind of things that we do here. We've got School of Telecoms Management, which deals a lot more with, should we say, management type topics. Or Telecoms Mini MBA is one of our very popular programs in that field. Perhaps the bit that I do most work for is the School of Advanced Communication Technology. So I'm more kind of heavily involved with technical aspects of LTE next generation systems and so on. Quite a lot of the programs that we do, distance learning included, in some of the classroom sessions. We've got this. We have an arrangement with Derby University as well, so it's possible to run through several of our programs and actually get some university accreditation for that. If you're interested in what we do, then of course you can find us online. There's some contact details there, telecomsacademy.com. I'll bring up this slide again at the end. So if you want to know more information about what we do, we can take you to the website. You can contact our sales teams directly. Now we're part of an organisation called Ovum, which again I'm sure you've probably heard of. And some of the information that we present in these Insight webinars are actually taken from the Ovum Knowledge Centre. So we have access to a lot of reports and so on that our analysts are putting together. So you'll see some of that being reflected in what we're going to talk about today. Well, let's get on with the session, really. Of course, we're calling this a high capacity access networks, and well, okay, mobile data. I think surely the message is clear by now. You've probably seen thousands of these slides, these kind of effects. Obviously, what we're trying to deal with here, well, I think the problem here is maybe twofold, threefold, maybe. The first thing to state is that there are more and more, smart devices being connected to the networks, and those smart devices are consuming more and more data from the network. We could have sort of lengthy discussions about what we think that is, but I think there maybe is a third aspect to this as well, perhaps not reflected directly in these various graphs, so that you can see stuff from Ericsson, from Ovum, from NGM, and so on. Everybody's making predictions about how much the traffic is growing. Maybe factored into some of those will be applications for next generation networks, and in particular next generation applications and services. So we'll talk about IoT and machine to machine and so on. That's going to place a lot of pressure on the networks, I think, moving forward. And I think it's really crucial because they're very specialist kind of applications. A lot of these, the Internet of Things, the machine to machine, very, very specialized kinds of applications. So I absolutely agree with most of you that wrote down there that quality of service is a really important thing for not necessarily increasing the capacity of the network, but just using what resources we have in a much more efficient and a much more streamlined fashion, very much application specific. So absolutely, we need more fundamental capacity in the network as well, although I may sort of tend to contradict myself a little bit here. So what do we need? Well, fundamentally, I suppose we could say we need more capacity. There's a very famous expression you can see on the page there. This, of course, is Shannon's law. So if we were interested about the capacity of a single system, a single transmission resource, we could do we could put some numbers and so on into that. But the suggestion seems to be that really what we do need, okay, is a large amount of bandwidth in the network combined with pretty good signal conditions out there in the radio interface, and the combination of those two things will give us, a certain amount of capacity in the system. But this is not the whole story, really, because there's only a certain amount you can do by just putting, this raw bandwidth into the system. There's obviously a lot more to it as we'll develop. So we could use that previous page and those arguments about Shannon's expression and signal to noise ratio, high capacity, high bandwidth, that kind of thing, to talk about and to justify why LTE is a good thing. I mean, if you like, moving through that evolution chain from 3G towards 4G and so on, then I suppose one of the key features of LTE is the fact that it supports a 20 megahertz channel, which of course is directly in support of that Shannon expression. We made a bigger bandwidth channel, compared to a 5 megahertz channel from the previous generation, from 3G systems. We support, of course, high high order modulation. We've got advanced antenna techniques in LTE, of course, MIMO. And LTE increasingly is showing support for new RAN architectures. So the idea of a small cells and a heterogeneous network and so on. So, LTE at this release that we have and a lot of the deployments that we see going on around the world are certainly bringing relatively high capacities to the front. So we're seeing between 60 and maybe 120 megabits per second, depending on where in the world we are and what kind of devices we've got and so on. So LTE is good, but we're going to say, well, okay, don't forget, IoT, machine to machine. There's and again, we've seen various predictions from the likes of Cisco and Ericsson and so on, saying that by 2030 there'll be this additional sort of 40 billion things that will be connected. Not all of those things will have to be connected through our cellular networks. Many of those can be done via Wi-Fi or slightly more small scale networks. But even if it was just another sort of 10 billion things to be connected through cellular networks, clearly there is a capacity element to that, not just in raw megabits per second that we would need to support, but just the management of how do we connect, a billion things to our network, and how do we manage that infrastructure and the billing associated with it and so on. So there are many problems or challenges that we'll face as moving forward, not least of which providing, relevant capacity in the access networks. For LTE and then LTE Advanced and those things going forward. So LTE is good, but of course, we still need to improve things, and we are improving things. 3GPP, they never sleep, it seems. We've got this constant release of new ideas and specifications. So the thing that we call LTE Advanced, and well, okay, maybe we can call that 4.5G. I think 3GPP have coined a new phrase recently called LTE Advanced Pro, okay, which is sort of a catch-all for a lot of the advanced features that we see coming out in association with LTE. But we've got release 10, release 11, we've got these yearly, well, not necessarily yearly releases, but they seem to come out fairly regularly. And there are some important features in here. I mean, if we just look at basic release 10, we'll say a few things about carrier aggregation and the MIMO techniques and so on. So you've got these, should we say, basic ideas of how can we improve the efficiency with which we use the radio spectrum, or how can we increase the amount of bandwidth available for various applications. But then sitting behind that, there are kind of really complex mechanisms that have to think about the interference within a system, and of course the quality of service that we've mentioned before. So a lot of the other features that you see in there, like enhanced control channels and interference coordination and so on, these are the things that we see in release 11. And further enhancements in release 12 and 13. A lot of these are sort of the supporting mechanisms to further improve the efficiency of our networks. And you see some key things out here in release 12, for example. So support of self-organizing, self-optimizing type networks, heterogeneous network services in there. And I think interesting, there's something to watch maybe out here in release 13 is sort of LTE in the unlicensed bands. So maybe up there in the 5 gigahertz band, we'll see LTE being used as an enhancement or an augmentation to the existing network capacity. But clearly there have to be standards set for that. It's not just about kind of tuning your radio to the 5 gigahertz band. So I mean that this is in release 13. I think we're calling it was it LTE-A, licensed license assisted access, I think is what we're referring to there. So there's a few new ideas which are coming out and have to be watched. But so okay, we call it 4.5G, call it LTE Advanced, but it has a really long lifetime. LTE, if you remember, has been around for about sort of since about 2009, so we'll say 5 or 6 years on that. But LTE Advanced is this sort of augmentation or enhancement to the network, which really is going to be with us probably for at least the next 10 years or so, I think. But I think the interesting thing about LTE Advanced as well is whatever we do in order to build that network is really going to form the basis of whatever we think the 5G system is going to look like. And a lot of the features that we're adding to the network to build efficiency or capacity, we're going to learn a lot by building these LTE advanced networks as we sort of head towards that 5G thing. We'll talk a little bit about 5G as we get towards the end of this towards the end of this session. But I thought I'd just briefly mention some of the things that we see being deployed around the world in respect of LTE Advanced. Now, carrier aggregation is kind of the big one, really. Any network operators in the world that are saying that they support LTE Advanced, or any devices which are supporting LTE Advanced, by and large, it's carrier aggregation is the thing. Now, we did mention before that LTE, basic LTE Release 8, Release 9 supports effectively a 20 megahertz channel, or up to a 20 megahertz channel. But what carrier aggregation allows us to do is to use those channels in an aggregated form to apparently give the device access to more than 20 megahertz of spectrum. So, I mean, the most extreme end of this, we've got we can support up to 5 20 megahertz channels, which of course will give us an aggregated carrier that looks something around about 100 megahertz. So it's a really important thing to do, because again, it solves that problem, that original Shannon expression, where we have more bandwidth. It doesn't really say anything about how efficiently we're going to use it, and of course there has to be control systems and channels and so on behind that, which enables us to use it efficiently. There's the added complication though, because when you think about all the possible frequency bands in which LTE is, well, even currently deployed, and all the possible bandwidths that are available, then there's a rather sort of a complex environment where we talk about the various band combinations. Now, you'll note the little website at the bottom there. I highly recommend, if you're interested in this, to go and look this up. I've just taken a couple of screenshots from there this morning. But we can aggregate two different frequency bands or two different radio bandwidths together to give us something like 40 megahertz of spectrum, or maybe only 20 megahertz of spectrum, depends on the frequency band and so on. But in order to get the maximum possible capacity out of these things, we mentioned before that we can have up to 5 possible so-called component carriers aggregated together, and those could come from, as the bottom table shows here, they could come from 4 different bands. So just this one example here, we've got band the 2100 megahertz band, 1800, 850, and a TD 2300 there, which can be aggregated together, really to give us something that looks like a 70 megahertz radio channel. So that's going to give us a ton of bandwidth, of course, and when combined with other techniques like high order modulation, LTE Advanced, I think in its most sort of extreme configurations, will certainly give us in excess of a gigabit per second in the access network. Now, a gigabit per second, some of you will recall, was actually was one of the qualifying thresholds that defines a technology as being 4G. So strictly speaking, LTE Advanced and using these techniques is really a 4G network. But we won't enter that particular discussion. Other things which are extremely useful, I mean, things like MIMO, of course, we have that already in LTE. Perhaps not the high order MIMO that we're talking about when we talk about else and so on. Certainly what we see at the moment is so-called 2x2 MIMO, which increase the air interface efficiency by between 60 and 80% maybe, depending on the actual location of the user and the antennas and so on in there. But this is taken further in LTE Advanced. So as I've called it here, high order MIMO, so 4x4 and 8x8. That will, again, that's not going to increase the throughput on the channel by a factor of 8. I mean, in the downlink direction, or a factor of 4 even in the uplink direction. Those things are not really practically possible. But what it does do is it massively increases the efficiency that's available to us in either the uplink or the downlink direction. Now notice here I'm using the word efficiency here in respect to MIMO, rather than, we kind of expect that it will increase the throughput, which it kind of does, but I prefer to think of MIMO as a way of just improving the efficiency. Because when you start looking at these very, very high data rates, which we, now when we've got, maybe 40 megahertz of aggregated spectrum and, up to 8 antennas being used to spatially multiplex the traffic down towards the mobile, we end up with these enormous data rates of 200, 300, 400 megabits per second. Now there are no applications that I can think of, at least, that absolutely need a couple of hundred megabits per second in the downlink direction. There are very few of these applications currently in the market. So I like to think of MIMO, and maybe some of the other techniques as well, as a way of increasing efficiency. Because if we have a data rate of, say, 200 megabits per second, then whatever data it is that needs to be sent to the mobile can be done in a much, much shorter period of time. And therefore we've got more time to deal with other subscribers that might be in the cell, or other devices that might be in the cell. So that's one way of thinking about the additional capacity that's really been brought by things like carrier aggregation and MIMO. So just an increased efficiency, increased spectral efficiency, maybe we could say, in conjunction with these techniques as well. And there are some practicalities when it comes to things like MIMOs. I mean, because obviously if we're talking about 8 by 8 MIMO, then that seems to suggest that there would be 8 transmitter points at the base station, and of course 8 receiving points in the user device. So in a small handheld device, the placement of antennas might cause us a few technical difficulties. But maybe these will be more suited to sort of specialist kinds of applications. Maybe CCTV systems that have to broadcast high definition streams, back to a control center and such like. So there may be some more specialist equipment or applications which would make more benefit of this idea, until we solve the problem of how do I physically place antennas into a small handheld device, at least. Another trend that we've been seeing a lot of is the idea of small cells, and it's been well understood for many, many years that if you want to increase the capacity of the network and in fact the spectral efficiency of the network, then what you will do is increase the reuse factor. So we can go back to the 1940s to find papers written by Bell Labs on this particular topic, but only really relatively recently has the technology been around that will allow us to build such small cells and to use very, very tight reuse patterns. So clearly small cells will provide us with, in the right environment, will provide us with improved coverage. I mean, indoors particularly. But remember, what you're doing by deploying a so-called small cell is that you are bringing the access point or the base station or the antenna much, much closer to the user. So if you think of a small cell being not much more than, say, 100 meters from the center point of the cell, then the users, the devices, of course, are much closer to the base station, and that's where we get this these additional efficiencies or throughput improvements. And because of the size of the area of coverage, we could probably argue as well that it allows us to create much better targeted capacity. So if we understand where the traffic hotspots are, which cafes and which corner of the shopping mall and so on, where these traffic hotspots occur, then of course we're able to target very, very with a deal of precision, and take the traffic from the larger cells of the network. So we can offload the traffic from the macro, the micro cells into this small cell layer. And just the very nature of small cells, as we mentioned, really just means that it's better spectrally efficient, because you're taking say 20 megahertz channel from the 2600 megahertz band, and you are reusing it many times over maybe even just a single square kilometer in the network. Of course, that isn't without challenges in terms of managing the power and the interference in the network, because we're not really doing frequency. We're not really doing frequency planning here. The intention would be that all of the cells would effectively be using the same radio frequency, or at least we should build a system that would allow us to use the same part of the radio spectrum for all of the cells, regardless of their hierarchy within the cell structure. We mentioned things like traffic offloading. Will improve cell edge performance. Sure, if we're using small cells as a mechanism of improving, say, a micro cell, so we're actually placing small cells at the edge of our macro or micro cells, then sure, we're improving what would perceive to be originally the cell edge performance. And it does rather interestingly yield something called CoMP, or coordinated multipoint. This is really the cooperation of multiple cells in providing a data service towards a user, and I'll say a little bit about that when we get to 5G, because it's something that's present also, although with a slightly different name in 5G. Small cells, though, a pretty challenging thing to do. Just the planning and design and deployment of small cells is, because we're dealing here with a lot of numbers. So where formerly we might have had, say, 5 macro cells, covering a downtown area, now we may be planning hundreds, if not thousands, of radio cells, both indoor and outdoor. So that sort of practical element of deployment and planning things like backhauling for these types of service, or you'll see the word front hauling being used as well in conjunction with small cells for certain types of applications. But the mobility as well, when you've got 500 cells per square kilometer, maybe in some extreme deployment, then of course you need to be able to manage the handover process and the resource management between the different layers of the cells. Security always is an issue, not just security for the subscriber connected to the small cell, but if you're bringing the cells closer to the street, and so you're essentially hanging it hanging these access points off of lighting structures and street furniture, then the physical security of those things as well is something that needs to be thought about as part of that deployment phase. And integrating those with the rest of the network. So if we're thinking about small cells from the point of view of a heterogeneous network, then those small cells, well, they may be LTE small cells or LTE Advanced small cells, but they could be other technologies as well. Wi-Fi is, I suppose, the original small cell in many ways. But how do we sort of integrate that more fully into the network so we can handle things like handovers between the Wi-Fi and the larger cell, and maintain things like security sessions or IP sessions as we move up and down these different network technology layers. So it's certainly not without challenges. We understand that, and I think the vendors understand this as well, because the comments have been made that it's the deployment of the things themselves, not the small cells, which are causing the problems. I mean, there are plenty of solutions out there, but the physical deployment of those. So one thing the vendors are playing quite a large part in is trying to simplify, or maybe the term we come across time and again is industrialize the deployment or the rollout of the small cells. So, for example, I mean, Cisco has a particular product, well, others do as well, but Cisco has a particular product that allows us to use sort of licensed LTE within their Wi-Fi services as well. I mean, you might say it the other way around, in fact, that there will be a Wi-Fi access point that also has LTE built into it. Ericsson has what they refer to as small cell as a service, maybe sort of leveraging that idea of cloud in the access network, which I'll say a bit more about in a moment. Nokia's got a deployment engine, HetNet engine room, designed to identify the assets, make the cells easier and quicker to deploy. And pretty much all the vendors have got some kind of physical solution that can be embedded in what we refer to as street furniture. So of course that's the street signage, the lighting poles and such like. So the vendors are trying to make it as easy as possible for the operators to deploy these small cell systems, because despite its difficulties, deployment difficulties, it's a very, very good way of enhancing network capacity. Don't forget that the other thing, well, one of the main reasons that small cells provides us with apparently more capacity, is the fact that if the cell itself is smaller and you are covering less meters squared on the ground, of course there'll be less people in it. And that means that each of the devices within that environment have a greater share of whatever available resources are present on that access point. And that's where we start seeing these sort of very high growth curves as far as the capacity of the network is concerned. But I think it was clear from our little survey just before the session, it's not just about the capacity. I mean, it's absolutely about quality of service, because we've over the years we've kind of, and this applies to fixed networks as well as mobile networks, cellular networks, and so on. But we kind of fixed the problem of quality, downloads failing or streaming buffering and that kind of thing. We solved that problem really by just making the pipes bigger. We go from a 5 megahertz pipe in UMTS to a 20 megahertz pipe in LTE, and then we got maybe up to 100 megahertz pipes in LTE Advanced. So by increasing the size of the pipe, we sort of delay the inevitable, that what we should really be doing is using the available resources as efficiently as possible, identifying the users or applications, and saying, this user or this application has a particular throughput or a delay requirement, or is particularly sensitive to errors and so on. And really what we're doing is we're trying to manage then the term that we tend to use these days is the quality of experience, which kind of that encompasses the user in this process as well. So as an efficient way of using available resources, then of course quality of service, quality of experience is a very good thing to do. Maybe the one thing that we haven't done until fairly recently is actually actively manage the experience of the users in the network. So I mean, the example everybody gives at this point is talking about like a gold, silver, bronze kind of subscription. And the gold user, of course, will have access to the highest throughputs and maybe the greatest quotas or volumes of data. But it could be down to sort of individual applications as well. So this means that the network equipment, both the front end of the network and the access network, but certainly the back end of the network as well, these equipments need to be somehow application sensitive. So we know the difference between a voice over IP call and a video stream and a download and just a general web browsing session and so on. So we can manipulate the resources available to those services and use those resources more efficiently. So it's an absolutely key thing to do. And of course the operators know this. Um, but you know, um, as well as sort of enhancing the network, it's we need these tools in the network that can allow us to identify the individual subscribers or perhaps the applications in order to directly control those processes. So we could talk to the vendors. We can sort of well, okay, things are in the standard that allows us to do this, but it's kind of up to the vendors and the operators to work together on the actual techniques, whether they are automatic or manual techniques of managing the capacity in the network. And part of this as well, I mean, we have this sort of final bullet point here that talks about this idea of self-organizing or maybe self-optimizing networks, depending on your point of view. Maybe either in a distributed sense, so each of the base stations effectively is to manage its own resources. I mean, that might make the network, should we say, slightly easier to build, because there's no really fine tuning that you would need to do or configuration of base stations during that installation or that deployment phase. But there's increased focus on things like centralized or a combination of the two, the hybrid self-organizing networks, where you've got more centralized control over what resources are being allocated, or perhaps what the traffic patterns look like within the network, and you're able to balance the needs of users in different areas of the network. Now, this is exactly how we do this automatically. How do we make more capacity or less interference available in different parts of the networks? Well, inevitably, this means that all of the base stations need to speak to each other, which if you remember within LTE, we have that so-called X2 interface, which allows the base stations at least some degree of interference management. But if we bring that right back into a central part of the network, then that gives that centralized control element perhaps a little bit more visibility of things like traffic patterns and interference and power that's being used by both the base stations and the users. Ideally, maybe a combination of those things, because centralized control is, should we say, a little bit overhead heavy, because there's a lot of messages that need to pass between the endpoint, the base station and the controller. So maybe you would have some sort of centralized feature, which is identifying or tracking, should we say, general KPI trends, but you've got the active management of resources which are taking place at the endpoint. So we can allow the base station to work in real time against a set of defined KPIs, but then that centralized point is receiving less real-time information in order to manage the general trend of resource efficiency in the network. And that's something that can sort of drive us towards this idea of providing the user with better experience as well, because we are, we're trying to control the access network in respect of its efficiencies. So there's quite a lot going on already within LTE and LTE Advanced in terms of deployments. But when we look out towards the next generation, it's pretty scary actually when you look at some of these numbers. Now, this is a document from the NGMN, and if you attended the 5G webinar or insight session that we did a few months ago, you may recognize this. Well, when you look at let's just look at this one here. So this is what they refer to as the use cases. So we have an indoor ultra-high broadband access, which maybe is the most challenging of all of the environments. So it's an indoor office type environment. But when you look at the data density in the downlink direction, so here we have 15 terabits per second per square kilometer. Now, again, this is shall we say, a loose identification of a kind of service that we might need to deploy. Broadband access in dense areas, 750 gigabits per second per square kilometer, maybe. Broadband access in a crowd, 3 terabits per second per square kilometer. So these are all big numbers. So, of course, what we need to start doing straight away is to think about, what kind of radio access network is it possible to deploy those kind of figures? So clearly some changes have to be made, maybe to both the architecture of our radio access network, but maybe even the radio interfaces and the amount of spectrum that we have to support those. So, I mean, just comparing with we've got released 12 capabilities. So we're looking here firmly at LTE Advanced as a comparison, but the improvement needed to meet those NGN requirements. Well, in terms of throughput, between 10 and 100 times improvement is expected. End-to-end latencies, 10 times improvement. Connection densities, 100 times improvement. So there's a lot of work to do, is really what we're saying. Now, this is really work being done towards 5G, of course, but another name for 5G at the moment is IMT 2020. Okay, so 2020, of course, being the date at which we expect 5G to become, more than just an idea. So we've got a bit of time. Well, okay, we've got 4 years or so to think about that. And in that 4 years, remember, what we'll be doing is continuing to deploy the LTE networks and optimizing those, but continuing to add LTE Advanced features to our networks in order to ramp up the capacity a bit. But the improvement dimensions, okay, network capabilities have highlighted here some of the current trends as we've identified. So network densification, of course, small cells, carrier aggregation is extremely popular. The MIMO and the CoMP, well, there's certainly the high order MIMO and the coordinated multi-point ideas. Those things are perhaps yet to come to commercial networks. But and something which network operators have been doing for quite a long time, the idea of traffic optimization, so network. But this kind of thing could also be done at the front end of the network, and an idea that we see for 5G is this idea of sort of caching, content caching, really in the access network. So there's quite a bit of work to do. Of course, the standards bodies, people like 3GPP and so on, are working on what those standard technologies should be. But at this stage, I would suggest that it's just they are just ideas. We won't know until about 2018, 2019, maybe when those actual standards will begin to emerge. But I think one thing that's going to be quite clear will be the physical architecture of the network. So, I mean, this is from South Korea Telecom. This is a white paper from South Korea Telecom, talking about the use of network function virtualization within the radio access network. Now, of course, the idea of NFV is not a new one. And, if you have in your network data centers or you've ever used the word cloud, well, then you know exactly what we're talking about here. But the idea of this moving towards the radio access network perhaps is a newer idea, and perhaps one which has not been fully implemented yet. But we might start talking, instead of talking about base stations now, maybe we'll just start referring to the remote radio unit, which is well, nothing much more than just an antenna, really, with some fancy electronics in there. But really, there's no control going on there. There's no termination of protocol stacks or signaling messages and so on. The job of this sort of remote radio unit is just to capture the radio spectrum and convert it into some form which can be transmitted through a network. And then pretty much all of the processing of that will be done within I hesitate to say a data center, but within some point conveniently within the access network. So there may be several of these. So you may have your sort of how should we say, I'll just put control here, okay, and then your control element goes out to multiple radio access points. Now that means that control point, centralized as it is between all of these remote radio units here, well, of course, it understands, well, how much power each access point is using, how many users are connected to each of those, what spectrum each of those is using. So it's able to manage the resources really from a centralized point of view. And if we make this thing kind of quality of service aware and so on, then we've really got good control of the flow and the use of resources right through the network. So this idea of having the base station in the cloud, at least the resource management and maybe some of the baseband processing could be done at this point in the network. No, actually, I mean, if I change the names of some of these, I mean, if I write here things like RNC, for example, then those of you from 3G background will know exactly where I'm coming from. But here we have the base station, which was not much more than the dumb access point, the node B, and we have the centralized controller. So it almost seems like we're going back that way, because the idea of LTE was to remove the controller as a centralized point within the access network and give that control to the base stations. And now we're kind of coming back a little way to this idea of having centralized control, which, I think combined with the idea of data center or cloud-like architectures gives us a slightly elevated view of the whole network, which is really what we need if we're going to effectively control and manage the resources over a relatively wide area. So within 5G, 5G will basically be cloud-based. I mean, the whole network will be, as far as we can tell for the time being, the whole network will be effectively in the cloud. So the core network, the services, the radio access control, all of that stuff will be, data centered effectively. But in the access network itself, when you actually start looking at the way that we're going to manage the radio interface to and from the users, well, there's some new-ish ideas coming out here. So this idea of device to device, in fact, we can find this in LTE already. We've got this idea called PROS or PROS. This is proximity services, which allows us to allow the users to communicate directly with each other, or maybe the users to communicate directly via a base station. So, we don't necessarily need the core network involved in that process. Um, so that's clearly an idea that we have already within LTE, and is something which is going to be important for public safety. They have to make use of these ideas of direct mode of communication and so on. But another idea is we're calling here content-centric networking. So, basically we have a big server down here at the base station, a big memory bank at the base station, in which we cache commonly accessed content. So this idea of shortest path delivery, what we would need if there's a viral video going around, for example, then we can push that out to the base station where we feel or we predict that there will be a high requirement to stream that content. So we stream it once to or we move it once to the base station, and then we can move it many, many times over the radio interface without using, again, the backhaul resources, the core network transmission resources. We already do something like this in that, rather than having to pull content from the internet all the time, so, from the YouTube data centers, we can cache the content either within the country in some cases, or we can cache it within the network, so we're not pulling it constantly from the internet and costing money. So the idea is just to push that a little bit further, so actually cache any content in the access network itself. Elastic cell. I mean, this is kind of sort of coordinated multipoint in a way. We've got we're moving from a cell-centric, because the idea with cell-centric is that you have a serving cell, okay, and the serving cell is entirely in charge of the control plane, the user plane towards that user. But the idea of user-centric means it doesn't really matter which base station the user is connected to in terms of the user plane. Maybe we would have a C-plane base station, so we have one base station that is in control of the control plane into signaling and so on. But for the user plane, it doesn't matter. Whatever base station is currently, or maybe I should use the term access point here. It feels more accurate to do that. But whichever access point is currently serving the user with the best radio signal is maybe the one we should use, because reducing the number of retransmissions is a good way of improving the efficiency of the network. And there are several things that we can do here. There's joint reception, joint transmission, and other ideas which enables to use multiple points in the network to transmit and receive. It's not an easy thing to do. Of course, we need highly accurate measurement, real-time reporting of information between the base stations, from the mobile to the base stations as well. So it's not an easy thing to do necessarily. This may be combined with things like carrier aggregation and heterogeneous network aggregation, using multiple layers within the network to serve the user at the same time. We talked about high density small cell. We just take it a step further within 5G. And then, because we're probably going to be using much, much higher radio frequencies, we're up there into the sort of, sub-millimeter band. Then we're able to make use of much cleverer antenna techniques. So, 3D beamforming, massive MIMO, as they call it, beam switching, tracking, those kind of things, which are ideal for very short range indoor type environments. So as you're walking around a conference room, for example, or even walking up and down an airport concourse, then there is effectively a beam which may track you from one cell to the next. Again, that's a fantastic way of improving the signal to noise ratio. And good signal to noise ratio, if you remember from Shannon's expression right back at the beginning of this, again, is one of the ways of improving the capacity for the users. We don't know about this bit yet, but there are some suggestions that we might have a slightly different multiple access mechanism. Of course, in 2G, 3G, we had CDMA. Okay, then we had OFDMA, a form of time division and frequency division multiple access. And then this sort of 5G idea, non-orthogonal multiple access. So really just doing a little bit of everything. So we've got codes in there, we've got time, we've got frequency, we've got complex methods of power control, which lead to methods of interference cancellation that we can build into that. So we don't know how that's going to work yet, but it's likely something that we'll see as a new radio access technique. I mean, combined with that as well, this idea of hybrid duplex and full duplex communications, because what we like to do at the moment is we like to separate the radio spectrum into an uplink band and a downlink band, or if we're using TDD, of course there is a time for the base station to transmit, and there will be a separate time for the mobile to transmit. But this idea that we can have in-band full duplex is just one of those things that leads to better spectral efficiency. That we don't need to worry too much about the guard bands and so on if we can make this kind of thing work. So there's some new ideas coming out for radio access techniques, but I think we're nearly done here. So just some final thoughts, really. That well, what we understand, applications and services, IoT, machine to machine, those things continue to challenge the network. But moving forward to sort of 5G, and probably the imperative for the CSPs, the communication service providers, is to think about support for the new verticals within those industries, within the IoT and the machine to machine. So we're only going to see more challenges. Remember, 40 billion connected things by 2030. It's the connected things for the most part will be, you know, machines and things connected to the internet, maybe refrigerators and such like, and vehicles probably an important one. And LTE Advanced we saw continues to play an important role in progressing not just the capacities of the radio access network, but the efficiencies that we can squeeze out of that. And it really lays the foundation for the next generation for 5G systems. But I think maybe key to it all really is maybe a sort of slightly high level view, step back and see what resources do we have and how can we use those things more efficiently. So I think my final point here sort of backs up what everybody said right at the beginning, which is sort of reassuring in that probably things like quality of service, proper engineered quality of service, application dependent, user dependent maybe in the network, that's really going to be a very important way of utilizing the resources that we have. Not saying it's going to be the easiest thing to do, because we need to understand, you know, what is a user or what is a device and what is an application, and what view do we have in the network of moderating the resources that each of those users has. So not necessarily the easiest thing to do. Certainly the best thing to do, because again we can solve the problem just by throwing more and more capacity or bandwidth at the system. But as we say, that's an expensive thing to do. You know, spectrum's expensive. I'm sure we all know that. But really, that's all I've got for you today. So really only a small session. But as you say, if you like what we do, or you want to find out more about what we do, then you've got our web address there, telecomsacademy.com, and there's an email address there to contact the team directly. Now I'm just going to drop in the middle here. If you want to see the slides, there's a